First of all, I would like to thank organizer arranging this nice event and allowing us to present our recent research here. So today I'm going to discuss advanced 4D-STEM analysis for mapping electromagnetic field and atomic structure, with a particular focus on how electron beam precession can help more quantitative 4D-STEM analysis. So idea of the 4D-STEM has been well introduced by previous speaker. So we have an array of local diffraction pattern from using 4D-STEM, which is combined information of the two-dimensional real space image and two-dimensional reciprocal space image. For our investigation, we use GTRX pixelated detector, which is the same as the tensor is utilizing. And for the electron beam precession, we use an omega system. For us, it has been quite challenging to work with two different companies, especially it's quite time-consuming, especially for the synchronizing issues. So for me, it's quite promising that Tescan already managed to combine these two techniques in a company level. I do believe this is quite big and significant progress, and also the large interest will be gained from the research community. And congratulations. So during the past years, we have been intensively utilizing and developing 4D-STEM technique. We started the 4D-STEM by mapping, by applying the common ACOM analysis and virtual imaging. Nowadays, for the amorphous system, we map the pair distribution function to investigate the short range and medium range structure of the complex system. And also we map the strain field to study deformation of the material. And also we map the characteristic structure, for example, magnetic and electric field. This is going to be the main topic today. And this leads to also mapping the distribution of the charge density within the material. And in principle, all the information from 4D-STEM can be simultaneously gained, because 4D-STEM data has contained simultaneously all this information. This leads to high-dimensional statistical analysis across the different structure information. And also here, the precision can be very helpful to obtain this kind of structure information in a way more quantitative manner. So today, using the precision-assisted 4D-STEM, I am going to introduce two exemplary research, one for amorphous system and one for crystal. For the amorphous system, I'm going to talk about deformation of the metallic glass by mapping pair distribution function and strain field. And for the crystal, I'm going to introduce the mapping electric field as similar to the previous speaker, so that we can map the space charges. Starting with amorphous metallic glass. Metallic glass is amorphous metallic alloy, which have been spotlighted past decade owing to their exceptionally high yield strengths. Take a look at this graph. Yield strength as a function of Young's modulus, and the metallic glass are the one highlighted in red here. The metallic glass exhibit way higher yield strength compared to any other kind of structural material we use in industry. This is we get benefit for the durability for the structural application and for the structural material. But the major problem of this material is limited ductility. They are brittle. The plastic deformation of metallic glass is accommodated by the formation of the shear band. So all the plastic strain localize and concentrate very limited and band-like volume, so-called shear band, and this leads to catastrophic and early failure of this material. As shear band play decisive role in the plasticity of the metallic glass, the understanding of the shear bending process has been one of the most important research direction in the glass community. The problem is the amorphous system has almost disordered and the dense atomic packing with interconnected cluster structure. So conventional imaging method, we cannot get the structure information much because there are lack of electron beam channeling. Also, there are too much overlapping of the amorphous structure. So here, the pair distribution function can be one of the powerful tools to study this kind of material. The pair distribution function can be obtained by the diffraction profile. By directly looking at the mathematical description, it contains two different factors. The first one is scattering from the singular atoms, so-called single atomic form factor. And the second term is describe the scattering from the solid, so-called structure factor. So this structure factor can be obtained from subtracting the background single atomic form factor from the intensity profile. Then thereby we for the real space representation we apply the Fourier transformation, that we get the pair distribution function. So pair distribution function, PDF, describe atomic density, relative atomic density as a function of atomic distance. Thereby, this peak represents the first nearest neighbor shell and the second nearest neighbor shell, so we can study short range and medium range structure of the amorphous system. This pair distribution function analysis become very powerful if we combine it with the 4D-STEM, where we can probe the local variation of the glass structure. So again, we have an array of the diffraction pattern, and we compute the pair distribution function from each diffraction pattern. By this, we reduce one dimension from the 4D-STEM. So eventually, we have a 3D or the layer cube. So XY contain the spatial information of the sample, and the Z-axis contain each PDFs. So by manually selecting reference, so we can study this PDF cube by manually selecting reference spectra, or if the structure is too much overlapping, the multivariate statistical analysis is quite helpful. For example, PCA analysis or ICA analysis and NMF. Then we get the reference PDFs, then multilinear scale fitting, then we can actually see their spatial distribution within the sample. But for the PDF calculation, it's very important. PDF require quite high signal, especially from the high angle, because all the fine feature in the real space. So high frequency information is stored easily visualized in the high angle. So to study the effect of the cutoff angle, so I artificially cut off the maximum scattering angle, and correspondingly I calculate the pair distribution function here. If you can see here, the pair distribution function, this one, with the limited maximum scattering information, the large scattering information from the large angle. So you will see you lose some the resolution for the fine feature. For example, here second peak separation is get reduced. So here, the electron beam precession can be quite helpful. So here is the two left-hand side have a two different structure factor, exactly identical imaging condition, and for the exactly identical sample, but without precession and with the precession. So you will see that the information cut off is much lower angle for the without precession compared to the with precession. Accordingly, if we calculate the pair distribution function, the second peak especially, so second peak separation, you can more clearly visualize this second peak shoulder. And this is particularly important for studying amorphous system because this second peak contains the medium range order information. So for studying shear band, we map the 4D-STEM PDF map here, where the shear band is crossing here, and we pick up the pair distribution function, the blue area and the red area, also in the core of the shear band, and visualize here. We see some small differences in the second nearest peak. So, but nevertheless, this small difference indicates quite significant structural difference within the glass matrix. Referring to the MD simulation result in the similar glass system, these some peaks in the second peak indicate the cluster connectivity shapes. For example, if two clusters share one atom, so we call this vortex sharing cluster, there the peak is located a little bit far distant. And for the two atom sharing cluster, then we call it edge sharing cluster, and is located here, and three atom sharing cluster face shared and located here. So our experimental result indicate that there are some different cluster connection shape in the respect to the shear band. For the more detailed analysis, we compute the ICA, the independent component analysis based on this 4D-STEM PDF data, and we confirm there are two dominant structural bases existing in the deformed glass matrix. One is IC1, which is dominant by the zircon bonding, and another is IC2, which is dominant by the zircon metallic bonding and metal-to-metal bonding. So by mean-splitting, we know that their spatial distribution. We confirm that based on the shear band, they are distributed asymmetrical way across the shear band. This indicates that the compression direction and the tension direction during the shear bending give rise to the different structural the medium range order within the glass. within the deformed metallic glass matrix. Also, we measure the fraction of them, and we also calculate the fitting error. And the fitting error, it has a high peak exactly at the shear band position. This indicates there's more structural variation occurred exactly at the shear band core. Referring to the MD simulation result, we can also map the map of the phase sharing motif here. So we can see that slightly reduction of the layer population here. This is actually makes sense from the theoretical expectation, because the phase sharing motifs is known as more stiff, and during the shear bending, they're more likely break. So if the shear bending occurred then there should be reduction of phase centering cluster. Adding to this pair distribution function analysis, we also map local string field by measuring elliptic deviation of the diffraction ring. So for this particular study, we measure the longest and the smallest radii of the diffraction ring to quantify two different principal strains. And with the pair distribution function analysis, we can actually get the string field and atomic packing density information simultaneously. This list gives rise to allow us the correlative analysis, how they are correlated in the spatial spatial distribution. For the strain mapping, we utilize advanced mathematical fitting methods, especially using linear algebra, so-called singular value decomposition. Based on the elliptic equation, we designed the fitting problem in the matrix multiplication way. And by solving eigenproblem of this matrix, give rise to the unbiased fitting, and also very computation efficient way to fit the data. So with this method, we fit the 500,000 diffraction pattern within several minutes with just a common personal computer. And also, this also leads to the improved precision for the strain measurements. Our upper limit of our precision measurement is below 0.05%. So here we map the 4D-STEM in the large field of view here across the several micrometer. This is one advantage of the 4D-STEM based strain mapping, where our field of view is actually unlimited. This is actually the high resolution based fitting strain mapping method cannot really get this kind of map. So we're going to have two principal strains. The principal strain 1 follow compressive direction, principal strain 2 follow tensor direction. So based on the two principal strains, and we map the volumetric and deviatoric strain, there we find two different shear band. For example, shear band 1 exhibit alternating fluctuation of the strain signal, and the shear band 2 exhibit linear band structure. To see shear information of the strains, so we calculate a strain tensor by setting coordinate system x-axis parallel to the shear band, y-axis perpendicular to the shear band. So echelon x-axis confirm that based on the shear offset here, one side is pushed down. This area we call the pop-in direction, we push down. There is suffer a compressive strain, and the other side is called the pop-outside is intention. And for the epsilon xy, which is a shear field, we found the zigzag arrange the feature. For the shear band 1, for shear band 2 is almost negligible feature. And for the epsilon yy, which is perpendicular component from the shear band, this is the alternating fluctuation along the band for shear band 1, and only linear band structure for shear band 2. To see more details of this deformation feature, we map the maximum shear strain, which follow the maximum shear strain direction, and with the amplitude is a deviatoric strain. So this area, this is visualized vector visualization with the arrowless stick here, and this small area where on the shear band and magnified here. So we interestingly see that with the shear field, there are quadrupolar strain distribution. Each quadrupole contains positive rings and the negative pairs of the shear field. So this means the clockwise and anti-clockwise shearing. At the center of the quadrupole, there is first nearest atomic, first nearest atomic distance, and in between the quadrupole is decreased first nearest atomic distance. And there we found that this maximum shear field is circularly rotating toward the adjacent quadrupoles and like in the vortex-like manner. So we quantify by line scanning along the shear bands and put a plot here. So we can qualitatively visualize and study deviatoric strain and volumetric strain, nearest atomic distance, and curve of the tau max, which means how strong the rotational field is. So maximum of the deviatoric strain coincides with the maximum of the volumetric and nearest atomic neighbor distance. And these peaks are separated by the strong rotational field. So I will not discuss much about the material scientific discovery because all of you have a different interest in the material science. But to conclude this part, this kind of analysis has been only done in simulation. Some of simulation results suggest and propose there should be quadruple defect in the glass matrix. But before this work, there is no any defect observed with the quadruple symmetry. But our work confirmed that, and their expectation is actually somehow correct. And they also some simulation work talked about their alignment behavior of the quadrupole to form the shear band, and our observation also gets showed a similar result. And this is also mapping the phase centering motif is also a first-time experimental visualization. Now I jump to the second part of the presentation, the mapping electric field and space charges. As like previous educational lecture, the mapping space charges is very of importance in the research community, especially for semiconducting, not only semiconductor, but any electronic material. For example, here I studied the electroceramic, so barium titanate and strontium titanate, and it is believed the grain boundary of the charge, space charge. Actually, the origin of this space charge is actually not well known until this is still in the discussion. But nevertheless, some simulation work and theoretical work proposed and some models, how they look like. For example, the double Schottky barrier model say the grain boundary is positively charged, and they produce the outward electric field. Thereby, any minus charge is go there because to compensate the charge. So, for example, if we accept the STO or BTO, then this minus ions in a high temperature, this minus ion goes to the grain boundary and they segregate there. This is just expectation from theory. But the problem is there have been no visualization of these space charges because the problem is this electric field is so big, so subtle, so we need a very highly accurate method to measure this. So we use 4D-STEM, precession assisted 4D-STEM. So already the mapping electric field is introduced by previous speaker, but the difference of our work is we do not use the central mass because we are hunting for a polycrystal. Polycrystal means different grain has a different diffraction condition. So if you use central mass, you will see just all the image, all the DPC signal is dominated by the diffraction contrast. So what we do is we apply the early age machine learning technique. Like here is a optimized binarization to get the only edge. So we smear out all the intensity information within the disk. We only get the edge, and based on this, we apply the algebraic method to fit this ring. With this, we got with the optimized binarization and SVD fitting. This does not suffer diffraction artifact anymore because we don't consider anymore for the intensity variation. But the precision of electric field measurement is around 0.6 millivolt per nanometer. This is enough small to see the space charge in electroceramics. So we compare two different methods for fitting the center position of the diffraction disk. Here's the mass center. For the polycrystalline material is dominated by the diffraction contrast. Here is Hopf transformation. But the problem of the Hopf transformation is accuracy is quite limited by its principle. But our new method is actually we reach the precision much smaller than the sub-pixel level. So now 9 times higher than the general Hubble transformation. So first, to confirm whether our new method is nice or not, we map the 4D-STEM in quite a large area across many different grains. So here is a without precision and with our new fitting method, and here is a with precision. So you see, without precision, diffraction, and with the precision, diffraction is much homogeneous. So this is a secondary phase. So the lattices one is so large, so diffraction density is overlapped with the convergence angle 2.5 millirad. So actually, anyway, we do not want to study these guys, but still, without precision, you see the diffraction artifacts occurred. But with the precision, with our new method, you see quite homogeneous, except this secondary phase. But as I told you, if we apply the center mass on 4D-STEM data, you see it suffers diffraction artifact so significantly with this method, actually quite difficult to map the electric field correctly. So arbitrarily just line scanning in some area, and we found that our new method with precision had quite homogeneous fluctuation along the large distance. But still, the challenging mapping this electric field is actually the judgment whether we clearly disentangle this diffraction artifact and the electric field information is not very straightforward. Even our new method, we are not so sure whether this is we have successfully done this. So we use some trick. We put the STM holder in TM, in situ STM holder. We apply the bias to the sample. So we expect the diffraction condition does not change much, but if there are space charge, then space charge can move from the external bias with the external bias under electron beam. So this is a DPC signal, the 0 volt and the 50 volt and 150 volt across the sharp grain boundary. And you see the variation of the DPC signal with the external bias. And this is, I calculate the X, like I set the coordinate system, the X-axis perpendicular to the grain boundary and Y-axis along the grain boundary, then see how they change. And their thickness somehow change. And this is one indication we might be correctly mapping the electric field out of many different diffraction artifacts. More details. So we zoom in the so we can calculate the electric field from, of course, from the DPC. And and the partial integration, what you call is IDPC, we can map this potential, and the partial derivative allow us to calculate the charge density. So we line scan across the shear band, across the grain boundary, and there we see this potential and electric field and charge density simultaneously. We can correlatively study the pixel level correlation. If you carefully see, there is outward electric field at the grain boundary, and there almost more than 20 nanometer the potential is built from the grain boundary. And this is a quite good match with the theoretical expectation. And we question ourselves whether this value is how much meaningful. And we just searched one previous calculation work, and we actually quite surprised because we expected still our method suffer some diffraction artifacts, so that this value should be much larger than theoretical values. But if you carefully see here potential, and this angle is actually how much different is a grain or mismatch with adjacent grains at the grain boundary. And this is change with the angle, but it's around 0 point something. But here it's also 0 point something, and the charge density also is the same order of magnitude. So still we are critically thinking about our new method nowadays, and we are planning to do the same measurement in different temperature. For example, cryogenic temperature to reduce any charging effect. And we want to also go up to 500 degrees Celsius, same measurement to reduce polarization effect. And we are also looking for the different types of grain boundary, whether this theoretical expectation happens. And we are also coating the sample to completely reduce the charging effect. Okay, with this, this leads to my conclusion and summary. So I introduced you advanced precision enhanced 4D-STEM analysis I introduced a highly sensitive measurement of atomic packing structure of amorphous system with the strain field. And this leads the first time experimental visualization of phase sensing motif and quadrupolar defect in the amorphous system. And I also showed the method to direct measurement of electric field and space charges. With this, I finish my presentation. I also thank all the people involved in this work, especially Lafayette has been a great advisor of our research work in a long time. Thank you very much, special thank. And also thank for your attention, and I look for your question now.
Thank you so much. So the first question comes from here.
Just a question or comment. Your method for finding the disks in the polycrystalline structure looks very much like Matus Kreinak's publication from 2016. Were you explicitly using their method?
Honestly, I don't know that publication. So which part?
So we've been, yeah, I mean, this bit where you're using this edge detection